Most parents think they're buying brain-building toys. What they're actually buying is expensive plastic that keeps kids quiet for 20 minutes. There's a massive difference, and it shows up years later when your teenager can't troubleshoot a problem or stick with anything hard for more than 5 minutes. I'm Rajiv Patel, and I've spent 15 years in systems integration watching which childhood experiences actually produce engineers who can think, and which ones just produce consumers with participation trophies. You're listening to the STEM Lab podcast. Quick note before we dive in, everything you're about to hear, all the research, the data, the script, that's written and verified by real people, by actual experts in the field. The voice you're hearing? That's AI generated. Just wanted to be upfront about that. Now, if you've been listening to this show for a while, thank you. I mean that. If you're new here, really glad you found us. We release new episodes every Monday, Wednesday, and Friday, and every single one is about translating STEM education into skills that actually matter for careers. So here's what we're covering today. The term 5 ways STEM toys boost your child's brain power has become shorthand in pediatric neuroscience for measurable cognitive improvements linked to structured engineering play. This isn't about making kids smarter in some vague way. It's about which neural pathways matter for jobs requiring systems thinking and which products actually train them. No developmental psychology jargon here, just the mechanisms that produce employable adults. So what actually qualifies as a brain-building STEM tool? Not every circuit kit or robot delivers cognitive gains. Real brain-building STEM products require 3 characteristics: open-ended problem spaces, meaning multiple solution paths, iterative failure cycles, those debug, test, retry loops, and skill transfer to industry-standard platforms. The Python versus Scratch decision for teaching AI to kids illustrates this perfectly. Scratch builds computational thinking through visual logic blocks, which is excellent for ages 6 to 9. Python syntax forces working memory engagement and abstract reasoning, critical after age 10. Both qualify as brain-building tools because they map to professional workflows. Block-based industrial automation interfaces on one hand, Python data pipelines on the other. Contrast this with battery-operated coding robots that execute pre-programmed light sequences, 0 working memory load, 0 failure resolution, pure entertainment value. Lab specs matter for repeatability. Products requiring proprietary consumables like specialty filament, branded battery packs, or cloud subscriptions for basic functionality create dependency, not capability. The Arduino starter kit runs on standard USB power, accepts any IDE supporting C++, and costs nothing beyond the initial hardware investment. Check the show notes for a link to the current price. That's a skill-building tool. A tablet app requiring $9.99 per month for premium lessons? That's a revenue model. Durability determines cost per learning hour. Injection-molded ABS components survive hundreds of assembly cycles. 3D printed PLA parts crack after a dozen. Sheet metal chassis outlast both. When you're evaluating brain-building potential, divide the purchase price by expected usage cycles, not by the child's current age. Now let's talk about how STEM tools physically alter neural architecture. These 5 mechanisms aren't metaphors, they're actual neurological processes. First, executive function development through constraint-based problem solving. Working memory capacity, holding multiple variables in mind while manipulating them, predicts adult income better than IQ scores do. Stanford's 2024 longitudinal study tracked 1,200 children from age 8 to 22. Students who spent 200+ hours on constraint-based engineering tasks showed 31% higher working memory scores at age 18 than matched controls. We're talking CAD design with dimensional limits, circuit design within power budgets, mechanical linkages meeting force requirements. Constraint-based problems force prefrontal cortex activation.
The child must simultaneously track design requirements, material properties, and solution attempts. Choosing a robotics kit for your child's skill level depends on matching constraint complexity to current working memory capacity. Too simple, like snap-together kits with one solution, provides no load. Too complex, like PCB design requiring Ohm's law calculations at age 7, overwhelms and shuts down engagement. I've watched this mechanism firsthand. My daughter spent 40 hours designing a motorized platform in Tinkercad that had to fit within a 10 cubic centimeter volume, lift 500 grams, and run on 2 AA batteries. She failed 14 times before a working prototype. Each iteration required holding gear ratios, torque calculations, and spatial constraints in active memory. Her standardized test scores in math problem-solving jumped 2 grade levels that year, not because Tinkercad teaches algebra, but because her prefrontal cortex had been forced to strengthen working memory pathways through repeated constraint satisfaction. Second mechanism, pattern recognition and abstraction via debugging cycles. Debugging is pattern matching under cognitive load. Every debug cycle, whether in code, circuits, or mechanical assemblies, trains the brain to compare expected versus actual states, hypothesize causes, and test interventions. MIT Media Lab's 2023 fMRI studies showed that children debugging Python scripts activated the same neural regions as professional software engineers. The angular gyrus for pattern recognition, dorsolateral prefrontal cortex for hypothesis generation, and anterior cingulate cortex for error detection. After 60 hours of debugging practice, children showed 28% faster activation of these regions when presented with novel logic problems.
This transfers directly to hiring outcomes. Enterprise systems integration, my field for 15 years, is 80% debugging and 20% new development. Junior engineers who spent childhood troubleshooting Raspberry Pi projects or repairing FDM printer jams debug production systems faster than computer science graduates who only wrote greenfield code in school. Understanding what FDM 3D printing is for kids covers the specific failure modes like layer adhesion, nozzle clogs, and bed leveling that train systematic troubleshooting. Concrete implementation here. The Elegoo Mars 3 Pro resin printer forces debugging through multiple subsystems: exposure timing, resin viscosity, support structures. Check the show notes for current pricing. It's messy. The learning curve is steep, but every failed print teaches the child to isolate variables, test hypotheses, and document solutions, exactly the workflow I use diagnosing API failures in production environments. Third, spatial reasoning and mental rotation through CAD workflows. Spatial reasoning predicts STEM career persistence better than math aptitude. Vanderbilt's 50-year longitudinal study tracking 5,000 gifted students found that spatial ability at age 13 predicted engineering careers more strongly than SAT math scores. CAD software forces mental rotation. Designing a bracket requires visualizing how 2D sketches extrude into 3D solids, how parts mate at different angles, and how assemblies move through space. Research published by the National Science Foundation in 2025 found that children who completed 40+ hours of CAD projects showed spatial reasoning gains equivalent to 2 standard deviations above peers, gains that persisted into adulthood. The training must involve actual constraint-based design, not pre-modeled assemblies. Snapping together virtual Legos teaches mouse skills, not spatial reasoning. Designing a functional gear train from primitive shapes like cylinders, extrusions, and revolves while maintaining proper clearances and ratios, that builds mental rotation capacity. I run my children through Fusion 360 projects starting at age 9. The software is free for students and uses the same interface as professional mechanical engineering teams. That matters. Learning Tinkercad's simplified UI means relearning everything when transitioning to professional tools. Learning Fusion 360 means they're already operating industry-standard software by middle school. Lab specs for CAD learning. Any machine running Windows 10 or 11, Mac OS 10.14 or later, Or Linux with 8 gigs or more of RAM handles Fusion 360. No subscription cost for students. Files export to STEP format readable by enterprise CAD systems. It's cloud-dependent, requires internet for saves, but offline mode works for 2-week intervals. This is the rare case where cloud dependency makes sense because collaboration features mirror professional workflows, where engineering teams share live model access. Fourth mechanism, hypothesis-driven thinking through citizen science protocols. Scientific method instruction fails when it's abstract. Teaching, observe, hypothesize, test, conclude as a memorization exercise produces students who ace worksheets but can't design experiments. The best citizen science kits for kids documents how water quality testing, air particulate monitoring, and soil microbiome analysis force real hypothesis formation. The child sees unexpected pH readings and must figure out why. That's genuine scientific reasoning under uncertainty. Johns Hopkins' 2024 study on 800 middle schoolers found that students conducting 20-plus citizen science experiments showed 40% improvement in experimental design competency compared to students receiving traditional lab instruction. The difference? Real-world data contains noise, confounding variables, and equipment limitations. Textbook labs provide sanitized results that confirm the expected answer. Implementation detail here. The Lamote Earth Force low-cost water monitoring kit tests pH, dissolved oxygen, nitrates, and turbidity using the same colorimetric methods as EPA-certified labs. Check the show notes for the link. Results feed into real datasets used by watershed management organizations. This isn't simulation. It's contributing to actual environmental monitoring while learning analytical chemistry fundamentals. The kit requires no consumable subscriptions. Test reagents cost around $25 annually for moderate use, works offline, and produces data compatible with Excel or Python pandas for analysis. That last point matters. Understanding skill milestones for 10-year-olds in STEM should include data analysis competency, and citizen science projects provide the raw data sets to practice on. Fifth mechanism. Delayed gratification and project persistence through multi-session builds. Grit predicts career outcomes independent of talent. Angela Duckworth's research across 15,000 subjects found that persistence toward long-term goals correlated more strongly with career achievement than IQ, SAT scores, or family income. Multi-session engineering projects requiring 10-plus hours to completion train delayed gratification at the neurological level. The child plans Monday's work knowing results won't appear until Friday. This builds dorsolateral prefrontal cortex connectivity associated with impulse control and long-term planning.
Short-cycle toys, 10-minute builds, and instant gratification projects don't activate these pathways. The brain needs sustained effort over days to strengthen persistence circuits. Real-world example from my testing process. I assigned my son a solar-powered vehicle project using raw components, solar cells, motors, wheels, chassis materials, rather than a kit. Completion required 4 weekends, 1 for design, 1 for assembly, 2 for troubleshooting gear ratios and weight distribution. He wanted to quit after the first failed test run. We documented the failure, calculated required gear reduction, ordered new components, and rebuilt. 6 months later, his teacher reported he was the only student who continued a failed science fair project into a second iteration rather than switching topics. That's the behavioral change this framework predicts: strengthened prefrontal persistence pathways generalizing across contexts. Lab specs for persistence training. Projects requiring assembly time over 10 hours, multiple subsystems like mechanical plus electrical plus software, and physical space for work in progress. Can't pack away nightly. Whether you need a dedicated STEM room versus multi-purpose learning space becomes relevant here. Projects requiring daily teardown see 60% lower completion rates because setup friction kills momentum. So why do these mechanisms matter for career outcomes? The connection between childhood neural development and adult employment isn't speculative. LinkedIn's 2025 Global Talent Report identified systems thinking, debugging competency, and cross-disciplinary integration as the top 3 skill gaps in engineering hires. These aren't taught in college. They're neural architectures built during childhood through thousands of small problem-solving cycles. Hiring reality check. I've conducted 200-plus technical interviews over 15 years. The candidates who excel aren't those with the most impressive credentials. They're the ones who learn to debug broken systems as children. They approach novel problems methodically because their brains developed error detection pathways early. They tolerate ambiguity because they spent childhoods working with incomplete information, troubleshooting circuits without schematics, designing mechanisms without explicit instructions. These 5 mechanisms translate directly to hiring criteria. Working memory capacity means managing multiple system variables during integration projects. Pattern recognition means diagnosing cross-platform bugs in production environments. Spatial reasoning means CAD/CAM workflows and mechanical system design. Hypothesis-driven thinking means A/B testing, experimental design in product development. Project persistence means shipping complex features across multi-quarter timelines. These aren't soft skills. They're measurable neural capabilities with quantifiable ROI in salary trajectories.
Let's talk about types of products that deliver versus those that don't. Not all STEM products produce the cognitive outcomes above. 3 categories. Tier 1, industry standard platforms, Arduino, Raspberry Pi, Fusion 360, Python environments, FDM 3D printers with open source firmware. These run the same software as professional environments, skills transferred directly to employment. Initial learning curves are steeper, but there's no toy ceiling requiring migration to adult tools later. Offline capable, expandable, repairable, no subscription dependencies for core functionality. Tier 2, proprietary but open-ended systems, Lego Mindstorms, Vex Robotics, Sphero programmable robots, proprietary hardware but genuine programming interfaces, either block-based or text-based code, support experimentation and failure cycles. Consumable costs are moderate, replacement parts available. Cloud features exist but aren't mandatory. These build legitimate computational thinking but may require platform migration around age 14 to 16 when students outgrow the ecosystem. Tier 3, closed entertainment systems. Battery-operated toys with coding marketing but no actual programming, just button sequences. App-dependent products requiring subscriptions for basic features. Single-solution kits with no variation possible. These don't train debugging because there are no failures, don't build working memory because there's no variable management, and don't transfer to professional tools. Pure consumption, not skill building. Durability and expandability separate tiers. Tier 1 products accept third-party components like standard sensors, motors, materials. Tier 3 products lock users into branded ecosystems. The complete 3D printer safety checklist for kids applies primarily to Tier 1 printers, open-source machines with exposed components and customizable firmware. Those safety considerations are the trade-off for unlimited expandability. Now for some frequently asked questions. What age should children start using STEM tools for brain development? Children can begin constraint-based problem-solving around age 5 to 6 with physical engineering toys, simple machines, gear sets, basic circuits. Transition to block-based programming at 6 to 8, Scratch and Blockly interfaces. And handle text-based coding and CAD by 9 to 11 if working memory capacity supports it. The key is matching cognitive load to current capability. Overload shuts down learning. Underload provides no growth stimulus. Test with small projects first. If the child completes tasks without visible effort, increase complexity. If they disengage within 10 minutes, reduce scope.
How many hours per week are needed to see cognitive improvements?
Stanford's longitudinal data showed measurable working memory gains at 3+ hours weekly of constraint-based STEM activity, with optimal gains around 6 to 8 hours weekly. Below 2 hours, neural pathway strengthening doesn't occur. There's a minimum activation threshold. Above 12 hours, gains plateau unless novelty increases, new project types, added complexity. Consistency matters more than total hours. 4 90-minute sessions outperform one 6-hour marathon because the brain consolidates learning during rest periods between sessions. Do screen-based STEM tools provide the same brain benefits as physical kits? CAD software and programming environments deliver working memory, pattern recognition, and hypothesis testing benefits comparable to physical builds. MIT's fMRI data shows similar neural activation patterns. Spatial reasoning develops slightly better with physical manipulation of 3D objects before age 10, then equalizes as abstract thinking matures. The main risk with screen-based tools is reduced debugging complexity. Digital undo buttons eliminate consequences, while physical builds force complete rebuilds after failures. Optimal approach? 60-40 split favoring physical builds before age 10, reversing to 60-40 screen-based after, as projects require CAD and coding integration. Can children develop these skills through school STEM programs alone? School programs provide exposure but rarely sufficient depth for neural pathway development. The average school STEM lab offers 2 to 3 hours monthly on rotating topics, below the threshold for working memory strengthening. Effective programs require 20+ hours on single project types before moving to new domains, allowing debugging patterns to solidify. Most schools lack this curricular space. Home supplementation provides the repetition cycles needed. That said, school programs excel at introducing tool categories like robotics, CAD, data science that parents then deepen at home with dedicated equipment. How do you measure whether a STEM product is actually improving cognitive ability versus just entertaining? Track 3 metrics: failure rate. Products producing 40 to 60% initial failure teach debugging. 90% plus success rates indicate insufficient challenge. Session persistence, child works 45+ minutes without breaks, suggests appropriate cognitive load. And skill transfer, can the child apply learned concepts to novel problems without instruction? If your child builds the same robot kit 5 times following instructions each time, that's entertainment. If they modify the design, troubleshoot custom additions, or apply learned principles to new projects, that's skill acquisition. Document projects monthly. Photograph builds, save code, record problem-solving conversations. Review after 6 months to assess whether complexity and independence are increasing.
Let me give you a developmental investment framework. These 5 mechanisms require viewing STEM products as neural development infrastructure, not toys. Calculate cost per capability gained, not cost per hour entertained. Decision framework I use. Does it run industry-standard software or proprietary interfaces? Can the child still use it productively in 3 to 4 years? Does it force debugging cycles or just execute pre-programmed behaviors? What's the expandability path? Third-party components or locked ecosystem? Total cost including consumables over 3 years. Products passing all 5 criteria justify premium pricing because they're building employable capabilities. Products failing points 1 through 3 are entertainment regardless of STEM branding. The hiring market in 2026 needs systems thinkers who can integrate across domains, debug complex failures, and persist through ambiguous problems. Those capabilities form between ages 6 and 16 through thousands of small engineering cycles. The right tools make that development systematic rather than accidental. Choose products that frustrate occasionally, require multi-session commitment, and produce genuine pride when they finally work. That's the neurological signature of capability building. Everything else is just consumption with better marketing.
That's it for this episode of the STEM Lab podcast. Appreciate you spending this time with me. New episodes drop every Monday, Wednesday, and Friday, so you'll never wait long for the next one. If this was useful, if it changed how you're thinking about STEM tools for your kids, I'd really appreciate a 5-star rating and a review. It's how other parents find the show, and honestly, it helps more than you'd think. And go ahead and hit subscribe or follow so you get notified the second a new episode goes live. Talk soon.